Okay, so let us start. So in feed-forward neural network, the weights are computed on the basis of the input propagating through neurons in the forward direction. In this, no neuron receives the modified input, right? So we will see the structure of the feed-forward neural network, and then there is a special algorithm which is applied even to feed-forward neural network, which is known as backpropagation. So this neural network algorithm has the processed input, which is cycled back again through the previous layer neurons, and the weights are modified. So let us look at this. Feed-forward neural networks will have weight learning only in one direction. So these are the weights which you can obtain using the gradient descent algorithm. And in the backpropagation neural network, what is happening is whatever results you are getting of the error, that is fed back and the new weights are obtained. We will have the details a little later, right? So the error E is computed, and then if error is greater than the tolerance limit, then weights are modified, and the weights, after the weights are modified, we keep checking it. So we keep checking it over the iterations, and then if error is less than the tolerance limit, then we terminate. So basically backpropagation will require lot of recycling of the error data to be done in order to update these weights, right? So you have already seen the function for delta W, so don't get confused with this minus sign. It is only the bullet that has been used for presentation. So the function g dash is 0 if g is not differentiable. So you must have studied in your school that the function which is differentiable has to have d of f by d of x existing, right? So d of f by d of x should exist. Can somebody give me the idea whether the function f of x equal to mod of x, whether this is differentiable or not? Can you draw the function and then find out what is the problem with this function? How do you define it actually? So yes, this is right. This function mod x is not differentiable because actually this function mod is defined as f of x equal to x for every value of x greater than 0, and this will be defined as minus x for every value of x less than this is f of x is, yes, minus x for every value of x being less than 0, and this is equal to 0 for x equals 0. It is actually this function. So when you draw this function on your coordinate plane, two-dimensional coordinate plane, what will it be like? It is, so if I am making the y-axis in the middle, where this center is the origin, then you can always draw this function. So if suppose x is 5, then the value of y, that is fx, is 5. And when the value of x is 4, the value of y is 4. So basically it is a linear function which passes through origin. So it is a line which is passing through origin, right? So when x becomes 0, it is 0. Now when x is equal to minus 2, right? So fx becomes minus 2, that is 2. When x is minus 5, fx becomes 5. So basically it is positive. Y value is positive even for all negative values. And you can see that this curve y equals fx equals mod of x has this kind of thing. There is a corner at x equals 0. So how do you visualize the differentiability of this curve? We cannot draw a tangent at the point of origin, right? So this you must have studied in your school mathematics. We say that the function is not differentiable at x equal to 0, right? So this is the function. This can never be a activation function. So what is the step function? Can you draw the step function on your sheet, right? So can g be a step function? This basically is representing the function which is still a step function. Of course, it is linear. So can you write a step function f of x equals, let us say 2 or 1 when x is greater than some threshold, and x is equal to fx is equal to 0 when x is less than or equal to some threshold, right? How will you draw this? The step function will be drawn as a step. Can you visualize this? Right, so let us draw this. So it says it is a function on this two-dimensional Cartesian plane, and you are trying to draw this function fx by this. Suppose our threshold was something like 10 or 5, the function will be like this. Okay, so can you see that this is differentiable or not? Are you able to see the curve in red color on the just immediately the course number, immediately above the course number? Are you able to see this figure? Is this differentiable? No, because at corner point there will not be a fixed tangent. There could be infinite number of tangents at the corner points. So for the calculation of delta W, for gradient descent method, we cannot use the step function, while earlier we were using the step function. Yes? Right, so there it is a function which is having a shape like this. So you can look at the function which I have drawn on the right of the slide. It is known as sigmoid function, right? The function name is sigmoid function, and it is differentiable at all the points, right? So this function has a form as this. I'll show you. This function has a form of y equals 1 divided by 1 plus e to the power minus x. Right. So this function is differentiable. You can always find the d of y by d of x using simple differentiation techniques. Based on that g dash function, multiplying it with the kth feature of the ith sample and multiplying that with the product of the error yi minus g, right? So then this thing is getting added over all the samples to obtain the weight, right? So one limitation of gradient descent method is that it should have a activation function which is differentiable. So step function is not differentiable, okay, and sigmoid function is differentiable, right? So this is one constraint, one limitation of the gradient descent method. It initializes weights in the n-dimensional space randomly. It computes the error E, right, defines the error tolerance limit, and when the error is greater than L, it modifies the weight W according to the delta rule. This is what is the crux of the gradient descent method. We have a mechanism to move in the gradient descent space, or the weight space rather we should say. It is the weight space where we are moving and we are using the heuristic of gradient descent. And then we compute the error with the modified weights and the given input. Okay, so yeah, of course, the kind of terminology I have taken is YI, while your Mitchell book, if you read, you get something of TD. TD is the output. Input vector is defined as XD. So input vector I have taken here in my description is XI. So it doesn't make any difference. Only thing is I'm presenting this here so that you have a comfort of correlating your understanding through the slides with your textbook reading. Right, so it is only a notion difference. So OD is actually the predicted output, right? TD is the actual target output. OD is predicted, right? So YI was the target and HW is the predicted. So for us, so this is how you can correlate and read through your Mitchell's book about gradient descent. So now, once the weights are obtained, what to do with these weights? So this is through the training. Where is the training data coming from? Training data is coming through the xi in the expression. You can recall, what is that? You can recall that this expression, the expression which is holding value using x of ik. This is the training data's xth kth feature. Then the computation of the weighted sum is with the ith training data. So x1, x2, x3, etc. are used here. Yi is the known target, that means target class. What is training data according to you? What is training data? How do you visualize training data used for the classification? Can you tell? So the training data is coming as a x and y pair, that you should recall. So x is the input describing the particular object being used for recognition. Y is its actual class. And then how is the object described? It is described through x1, x2, x3, etc. These xi's are the features. So we will call this a feature vector. You remember this? Feature vector. So this was used as a training. So basically x is this x1, x2, x3, right? So and then y is the actual training output, right? So actual training class. We know this through our validation set or through our training set. So actual training class label. Okay, label also I should add, because it is just not the name, it is some identity of the class. So this is what is the training data. Training data is being used at the computation of HWXI, where all x1 to xn values will be utilized along with the weights. Which are these weights? HWXI. Which are these weights? At a point where you already have an older set of W1, W2, Wn, that set of weights is used in combination with x1, x2, x3, xn to compute the weighted sum as W1, x1, W2, x plus W2, x2 plus W3, x3 plus W3, xn. So this is basically a computation based on the older values of W in the previous iteration. Y1 is actually the actual class. It doesn't get changed every time. It is just the actual class. It is known for the data x1, x2, xn. And this xk is the kth feature of the ith samples. That is how we compute wk. So now you have understood that the training data is used. Training data is used in computing the weights, because at some point of time you will terminate the search. So as a result of this training, you get the final parameters W1, W2, W3, Wn. This is not intermediate. Intermediate values were old and new and getting corrected every iteration, and at some point of time you converged to the final value of W1, W2, etc. This is the final weight. Now no more iterations. So then we have a new feature vector which is to be used for testing. This one we do not have its y correspondingly with us. This is a unseen sample. When I say that this is unseen, this means that we do not know its class. Not know its class. Okay, this is what it means by unseen data. But any data which is there, I am able to calculate x1, x2, x3, etc. and xn. Why is it possible? Suppose you are measuring the class of a apple. Suppose it is a fruit classification problem. You are classifying a fruit. That fruit is there with you, with your machine. So it will be having its computations using the modules to compute the sizes, the texture, etc. of the fruit. So x1, x2, xn, etc. are known, but the machine doesn't know by now whether it is an orange or whether it is an apple. This it will know only when this x1, x2, xn, etc. will be now subjected for testing. So how is the testing done? It is done through the same simple formula here. You know that W1, W2, etc. are already known through training. Okay, this is through the gradient descent algorithm, and these x1, x2, x3, xn, etc. are being used of the object that has to be recognized, right? x1, x2, xn are not coming now from the training data. Training data anyhow we use for the computation of weights. Now this unseen data which is appearing for its classification, we want to find out its y. So x1, x2, etc. are used for the test data, and W1, W2, Wn are the learned weights. Basically machine has learned to differentiate between two classes or many classes only through these weights. Now whatever this y value will be computed, this will correspond to the closest class for the unseen data. Right, so if it is a two-class classification, it may represent a y as something like 1 or 2. So basically here I forgot to mention the activation function also. So y is basically an activation of activation G applied on H. So this you should correct here. G is applied on H. So basically whatever weighted sum you are getting here, you will also apply the activation function, and then it will get you the output as y. So this is the identification or recognition of the output. So then we say that machine has learned and has responded. So through computation of y, the machine has responded in telling what this object should be. Right? Is there any doubt? Any doubt so far? Okay, so we move ahead. So this, yeah. What is it that you are not clear about, Biswajit? This process of learning? Okay. So by now you are clear that you have learned weights. Is this part clear? You have learned the weights through the training. Okay. So once you have in hand the weights, they are capable of discriminating the objects in the environment that you have modeled here. Right. What is the modeling based on? Modeling is based on the training data set through which we acquired these weights. So I would say that this is the knowledge, right? W is the knowledge. Basically all these parameters are the knowledge. So once the machine has this knowledge about the discrimination between orange and apple, or a person by face, the difference is known, and then if the machine is able to understand who is who, then it can recognize a new face or a new fruit in the fruit recognition problem. So once W's are there, for a unseen data, which is this, I'm taking this as unseen. Now this is not a training data. This is the testing data. So what you are seeing here at second point is the testing data. And testing data's X value only. That is available. Y is not available. Now how to compute this Y? This is through the weighted sum. And this weighted sum is computed using these two information values. One is this weight, which you have learned, right? And then the other is the testing data X value. Through this, we are computing the weighted sum. And then you apply the G here, okay? Then you apply the G, that is the activation function, which I forgot to mention here. So prior to HW, you must have G. With this G, you have computed a Y. That means now your machine knows its class. So Y is basically the class label for the unseen data. That is how your machine has learned and responded its learning, right? Okay, so I hope others are also clear about this. Okay. Okay, fine. Yeah. So now we come to this multi-layer feed-forward neural network. These represent the class of networks which approximate the complex functions. Of course, they are good in modeling the non-linear decision boundaries, right? Because we have multiple layers, they can represent the non-linearity of the decision boundary. We saw examples in the very first class on neural network, and we saw that simple linear decision boundary can be implemented by 2 neurons or 1 neuron, right? But a non-linearity can also be handled by more layers in the neural network. So the network has one or more hidden layers. The neuron I of layer L is connected by a synaptic weight WKI to the kth neuron of layer L plus 1. So it is just a notion of representing the weights. This also we could touch upon, but then we could not talk much in detail. So W21. Why should it be 2? First, because the next layer neuron, the second neuron, is connected to the first neuron at the first layer. So that is why the index of the next layer's neuron comes first here, and the index of the neuron at the previous layer comes later. That is one notion that is followed mostly uniformly. But if you write W12, then also there is not a problem, right? So this is the input layer, hidden layer, and output layer. So the information flows from the neurons from one layer to another layer. You should understand that the intermediate layer, the middle layer, is the main layer for the computation of the new inputs, computation of the new information. So yeah, it is called hidden layer because it is internally calculating certain things and then bringing out the output to the output layer. How this is calculating, how complex this could be, and this is the term given by some AI experts who were involved right in the beginning of building up the neural network technology. So it is quite common to use the intermediate layers, hidden layers, right? Otherwise, you can also understand that this could be the processing layer. The one very first is the input. So I'm assuming the data is coming from left to right. So the output layer is the extreme right layer, and the extreme left layer is the input layer. Okay, so the extreme left is the input layer. And then we go to the different inputs. You have the simple nomenclature, the neurons, They have information flow to all intermediate nodes. So the hidden neurons will get, so all the neurons in the hidden layer are also called as hidden neurons. Yes, so multi-layer perceptron has the abbreviation as MLP. So yeah, this should have been a capital L. Yeah, that's not a problem. So then each neuron in the input layer would also be contributing to the middle layer, the hidden layer. Similarly, you will see that that all the neurons in the input layer would be contributing to one neuron as well, right? So every neuron in the input layer contributes to every neuron in the hidden layer. Hidden layer computes its output for each, each of these output neurons as the weighted sum of all. So what you can visualize here is basically G of H of, right, H of W, okay, H of W. So I'm writing W without a subscript, but you understand that it is meant to be only giving you the computed output, or it could have been just the weighted sum. So W1 X1 plus W2 X2, right, plus W3 X3 plus W4 X4. And based on the notion of your W1, this could have been actually W11 X1 plus W12 X2 plus W13 X3 plus W14 X4. If we base our notations based on the logic that I gave a little earlier. So this way, this will be the output by this neuron. Okay, the neuron right here will be producing this output, and this output will be processed by either using one activation function, or directly it will be going and get added by one more weight at the later layer. Suppose I call it W something, let us say W7, right? So this one will actually get added with the weight as W7, and what my first output neuron, this one, will be receiving, will actually have the outputs from each of these hidden neurons getting multiplied by their corresponding weights. So each line here is a synaptic weight. It will have its own corresponding weight, and the corresponding output, which is nothing but the weighted sum, will get multiplied, and another expression will come up of the form W1, right? So W7, let us say I'm taking for example W7 as that link, getting multiplied by W1 X1 plus W2 X2 plus W3 X3 plus W4 X4. So this is one thing that gets added to, let us say, W8 for the next link. Okay, so this will get added to W8 multiplied by some term which is coming up as the output of the second neuron, plus W9 multiplied by another term, right? So that way you can see that we are building an expression, quadratic in W, is it not? Now we are building an expression which is quadratic in W. W7 W1, W7 W2, W7 multiplied by W3, and this is a kind of non-linearity that we are bringing in the network. Any non-linear boundary can well be handled by the degree of the polynomial that it has. If the polynomial is so complex, I show you one example. If suppose my data was something like this, I am again drawing some very simple figure. on the right hand side of your screen. So I'm changing the color for a different class data. Okay. So are you able to see this separation of red and blue points? Then if I draw one line or one non-linear boundary, it will be something like this. This is quite non-linear, but not heavily non-linear, right? It could be a polynomial of first degree. You can even relate it to the hyperbola or parabola or ellipse that you had studied earlier. So what we see on the screen as a decision boundary separating these two types of points, we can say that this is a second degree polynomial, right? What we were having that expression were actually representing such kind of boundary. Now, if I'm having more complexity, okay, suppose I'm having more complexity of this form that, I am having more, I'll show you. So if I'm having more, complex boundary, right? And then I'm having the boundary being drawn as this, right? Maybe we'll see it a little later. I will make it active. So are you able to see this boundary having, different curves somewhere around the newly created blue points? This creates more nonlinearity in the classifier. That means our data is so heavily mixed and it is not at all able to be separable. It is not able to separate itself by the simple decision boundary of second order polynomial. That means now we have to incorporate more layers in the neural network to handle such kind of nonlinearity. We cannot do with one simple line form of the slope and intercept. We cannot just simply do by two-dimensional weight space. Our new layer, one more layer we could have created. You could have seen that, we can have another layer in between with more neurons, right? And more connections. So I'll show you more connections. So if there are these neurons, then you can have more connections. Okay. Similarly, other neurons will also be passing information to the new layer. So that means if there are two hidden layers, then we can handle at least more nonlinearity. But it means the increase in the weight space dimension. Are you getting this point? Now let us talk about weight space dimension. What is happening here is, you can understand that if this input layer has 4 neurons in it, the hidden layer has 5 neurons in it, okay, and the output layer has 3 neurons in it, okay. How many weights will we have in total? Can you tell? How many weights between input layer and hidden layer? Anybody? Please tell. So it will not be 4 into 5 into 3. It will be 4 into 5 plus 5 into 3. Okay. So it is 4 into 5 for the first 2 layers in between. You can always count on this. It is 5 plus 5 plus 5 plus 5. That means it is this much. And the hidden layer and output layer will have a total of 5 into 3 neurons. Correct? So in total, sorry, the weights, not the neurons, but the weights. So the total weights will be equal to 35. So now you can understand the complexity of your neural network. It says that the weight space dimension itself is 35. Now you can see from the two-dimensional weight space which we were talking about a little earlier, now we have to go for a 35-dimensional weight space For all such weights W1, W2, W3, W34, W35, everywhere we will have to apply the delta rule to obtain a new set of W parameters, right? And that too will be getting us only something which is having some error. We may get stuck in the local optima, we may not be there for the global optima and so on. So we will have 35 steps, not the gradient. 35 algorithms cannot be there. It is only one algorithm which has a delta rule that says new value of W, right, in the K direction. So whichever way you want to write, you can always write new of W in every direction is equal to old W, okay, plus or minus delta W, right? So I'm writing it as delta W, right? So this is how you will be doing it for all 35 directions. So it will be, if you take this as K, right, old WK and delta WK, then this K value will be varying from 1 to 35. This is just one algorithm, but you have to keep updating those 35 weights every time till your algorithm converges to a minimum error. You can always have a threshold for that. So this way it becomes a very, very complicated work. More nonlinearity means more layers. Suppose you have another layer of size in between, I'm saying. So suppose you have another layer in between of size, I must say it is, let us say it is 7, right? So if it is 7, what will be the total number of weights? What will be the weight space dimension total? Can you tell now? 4 into 5 plus 5 into 7 plus 7 into 3, right? How will it be? So if it is 7 in between, that means every neuron will be having the weights to those neurons. So 5 weights to 1, and there will be 7 such neurons. So that means the 35 themselves are between layer 1 and layer 2. What about input layer and layer 1? So the very first layer with 5 neurons I am taking as layer 1. The second layer with 7 neurons I am taking as layer 2. So between input layer and hidden layer 1, there will be 20 weights. Layer 1 and layer 2, it will be 35. And layer 2 to output, it is 21. Good. So then it becomes actually very heavy. So its weight space becomes so heavy, as large as I think 76 dimensional weight space. Just to have these two layers. So how do we decide how many layers we need to build for a classification problem? This all depends. That is where you want your system to learn. It is not we as humans who know the underlying complexity of the data. We do not know how much nonlinearity would be existing within a 100-dimensional space of input. So we want our systems to be able to learn themselves, evolve themselves. So nowadays the research is going on in having evolvable structures or the self-organizing structures. So they organize themselves to find out how many layers they can have. See, when you learn a term like deep learning, you should understand that deep learning starts when you have more than 3 layers. And if you have 3 layers represented by some hundreds of neurons, you can understand the complexity of the underlying weight space. So when the space is so complex, you cannot travel that complete undulations of the three of those n-dimensional weight space. In those cases, rather than gradient descent, people go for approximation algorithms. More approximation algorithms will tend you to get you to close to the global optima in less time. So there will be, in this example, 4 plus 5 is 20, 4 into 5 is 20, 5 into 7 is 35, and 35 into 7 into 3 is 21. So 20 plus 35 is 55, plus 21, it is 76. So here you will have this loop condition getting changed to 1 to 76. All 76 weights will be changed in the one iteration of gradient descent. Fine. So is it 4 weights in first iteration for first neuron? No, not like that. All the weights will be changed. Okay. So it all depends on how you are moving with the information. Fine. Okay. So I'm moving to the next slide. So multi-layer perceptrons, these are the acyclic directed graphs, and MLP is a feed-forward neural network, and it can handle non-linearly separable data. It has different hidden layers of neurons which process the data, and training is through weight learning. So ith layer passes the information to the I plus 1th layer. Okay. So then we have this real world problem, the face recognition. Okay. So what is a face for a computer? It is only the numbers. Have you ever taken the image and seen its values in some kind of software like MATLAB or anywhere? The values appear like these. These are nothing but the quantized intensity values. Quantized values are because you must be having a digital camera. So there is nothing like analog. We have the digital camera, and then the face image which is being imaged reflects the light falling on it, and then whatever light is reflected back onto the camera records the details of the intensity, and then it has its own procedure of quantizing this in say 256 levels or 512 levels, right? So more is the resolution, more is the picture quality, and so on. So again, based on that, you get the complete image as this. So looking at this image, can we say whose face image it is? We cannot say whose face image it is, and the patterns could be very, very difficult to be found. We are not even able to see the eye or nose or mouth or cheeks of any person. So it is so blind for a computer to identify who this person is. But when a person is imaged, probably certain areas like this may have some specific patterns. It will come something like 204, 208, 220, then 180, 120, and so on, depending upon how much light is falling on the face and what is the face pose and other things. But what doesn't change is the underlying, bone structure of the face. The structure of the face doesn't change. That creates similar patterns in the image, irrespective of whatever light and whatever pose it is. Of course, it is quite challenging for a computer to understand the patterns. I can tell that this is person X image, right? Some person name I can give, some person ID I can give. And if I tell this, that this is person ID 1, maybe tomorrow I give another face image and I tell this is person ID 2, maybe 100 faces I use for 2 persons, taken in different imaging conditions, different light conditions, different poses, different expressions. But I keep telling my computer, see, if you are seeing these numbers, this is person 1. If you see these numbers, this is person 2, and so on. So what it does, is that it tries to extract the features and it learns who is person 1 and who is person 2, right? And then it extracts the patterns, places them in the classifier, and then classifies the unknown person's image for whom we do not know the person ID. So we cannot really say whether it is this person or that person. So for humans, it is the face is like this with 2 eyes, nose, mouth, cheeks. Whether it is person A, person B, person C, this is the data set which I have used from ORL face repository, right? So whose face is this? Machine can recognize if trained, right? So then patterns for humans could be eyes as a right? But a pattern for a computer is the sequence of numbers. This is what is the feature vector that it has to build. X1, X2, X3, etc. It may try to understand that, okay, I will be picking up these 4 values. After that, I will be picking up these 4 values, and then I will be picking up these 6 values. Let us say. So that means 197, 188, 186, 171, 206, 207, 205, 205, 208, 195, that etc. makes it a feature vector for one person whose name we have already used as yi to train our system. Now its responsibility will be to compute the weights and pick up the same features for the unknown face image and then classify. Okay, so which pattern of numeric values represents a person's face uniquely? Okay, so humans' face recognition ability is amazing. With the spectacles, with the different expressions, we can still recognize this is person B, right? But it is still a challenge for a computer to handle spectacles, any accessories, any huge expressions or huge poses, right? So that way you will have to see that you train well your system with more sophisticated algorithms, right? This thing I have already discussed, so I'll just go through reading it. So it is simply a grid of numeric values for the machine. Machine uses its computational powers to identify patterns from the above numeric values. This is what is feature extraction, and these patterns are unique to a person. Okay, a face image is represented by various numerical ways such as PCA, eigenfaces, DCT, wavelets, and other statistical methods. Even I discussed this earlier that DCT and wavelets, etc. will be there in the domain of image processing. If you are interested, you can do some independent courses on image processing to be able to understand features for images. Okay. You have understood the pattern, so 1, 2, 3, 1, 4, 9. If I'm having class 2 as 1, 4, 9 and class 3 as 1, -1, -3, -5 with these values, and if I give you a test feature vector, what will you understand out of this? So these are the consecutive integers. This is one pattern. Squares of consecutive integers. This is another pattern. And descending integers with a step size 2, this is another pattern. So if I'm having a test pattern as 25, 36, 49, what would I understand about its class? This itself is a representative of the squares of some values. I would say that this pattern belongs to class 2, right? So basically, the patterns need to be extracted well, and then they should be used as the feature vector to get recognized by the machine. So humans recognize easily because they have good generalization ability, right? So there is always an effort in the machine learning community to make the system with large generalization abilities. Okay, so machines need mathematical models to recognize patterns. You have understood the patterns. These are the individual values in the pattern. They do not give valuable information individual values will not give the information about the pattern. So all values in association with each other are informative, and patterns have an underlying mathematical structure. Complexity of the phase data. The geometric phase features are not robust with respect to variations in expression or elimination conditions. If you're looking at the eye as a geometric feature, eye may become small or wide depending upon the expression, if the person is laughing or sad. The overall geometric features calculated in terms of shape of eye or width of eye, etc. may change. So that is why we say that these features are not robust. And then we need to go for some kind of mathematical representations such as coefficients of the discrete cosine transform, wavelet transform, etc. And they used to be represented. Yes, so yeah, the Chinese face recognition problem is quite well researched on, I think, Jaffe data set or something they name it as. So a large number of research papers you will find on Chinese face recognition problem as well, right? So mathematical representations need to be used for representing the face image. So a large number of such coefficients would be required to retain identity of a person. A small number of best features are selected to reduce the computational load. The number of optimal features is also very high. We can take, just 45 discrete cosine transforms to represent the complete image. As I told you in one of the previous classes, I remember that the JPEG format used earlier, the DCT, and a very small number of coefficients as against the total image size was used to transmit it from one computer to another over the network, and the compression rate was quite very high, even as high as 97%. That means only 3% of the data is sent and retrieved back at the other end without much loss of information. The loss of information could hardly be 3% of the total picture quality. So that is how only very small number of discrete cosine transforms can also coefficients can also be used to represent the face of a person, and this will act as a feature vector, right? So instead of saying best, we call it optimal because there is nothing like best features, right? So if you take some non-phase data, maybe a table, a glass, or a water bottle, they may be quite highly separable in the three-dimensional space or n-dimensional space. But if you look at face data, each face is a point in n-dimensional space, and they are quite mixed up because all of our faces are almost similar. Unless carefully selected, we cannot discriminate between people by faces. But human intelligence is much larger than we can create in the AI systems or machine learning systems. That is where the real research comes, where you have to understand each person's face data thoroughly using some feature extraction techniques, and then you have to identify those features which are the most discriminative, right? Otherwise, if I look at the same ORL face data set, which is available at the machine learning repository of UCI Berkeley, you can download this data, or it is also available at different other websites of face recognition. You will see that if you represent them in three-dimensional space, the 40% images are falling as the points like this, which is not just nonlinear. It is impossible to distinguish between the names or the identity of the persons, right? So in the face recognition problem, not just the decision boundary is important. It is also important about which features to extract and which features to select out of the extracted features, okay? So then, because this is non-linearly separable, we have certain different mechanisms that can create boundaries between the clusters. There could be a spherical boundary, there could be a planar boundary, there could be different other boundaries as well, right? So let us say this red point is the test data, right? It is also plotting on the same space, but where does it belong to? So we can have possible decision boundaries which are either defined by hyperplane or hypersphere or Gaussian surface or support vectors. Okay, support vector machines would actually be having the maximum margin between the two classes. So we will be talking about those in some future classes. So challenge is about the design of the decision boundary. Okay. So you have understood that face recognition problem is posed as a classification problem. Classes are the person names, identity, and training face images are visualized as points in d-dimensional space. Challenge is in identifying appropriate demarcating individual cluster. Okay. And then there is another feed-forward neural network architecture, which is known as radial basis functions neural network. What happens here is that this is also a neural network with one hidden layer. The activation function at each neuron is not similar, it is different. So what happens is that these units in between the neurons are known as radial basis function units. And then you have this space, which is the weight space, which is used for computation of the output. So the question comes, why we should have more neurons if we have more number of classes, if we have large input sizes of the patterns, okay, and when nonlinear separability of clusters in n-dimensional space. So then we need more neurons. RBFNNs capture the training environment in terms of weights. The radial basis function units, RBFU, locally capture the structure of the data. So basis functions at the RBFU play an important role in transforming the non-linearly separable high dimensional data to a space of linearly separable data. This is very important that here at each neuron, let me come back to the figure, each neuron has some kind of mapping system which takes as input the non-linearly separable data x1 to xt and maps it into the space where it is linearly separable by way of applying some kernel functions. Okay. So here we have a slight comparison of multilayer perceptron versus RBFNN. If you have this type of data, one with the blue dots and the other with the green squares, if you have a decision boundary as hyperplane, you would separate the two classes with full accuracy as this, right? And if it is a decision boundary is a radial basis function neural network, it will capture these subclusters, and then any data which comes as the testing data would be seen for its belongingness in one of these clusters, and then the corresponding class will be assigned to that. Okay, so these are called as the decision boundary, which is hypersphere. Okay, so the center of the natural cluster is the center of the hidden neuron. A hidden neuron is sensitive for data points near its center. That is what is the beauty of this RBFNN, that it localizes. So anything which is close to this, even the test sample is close to this, it will have the belongingness to this cluster, right? So you can always model this do not know condition. You may want some kind of rejection of the test feature vector to be not belonging to any one of the classes. So this can well be handled by the neural network of basis function. If it is beyond the decision boundaries which are spherical in nature, then we can simply say that I do not know who this is. Fine. So I think we can stop here, and then we will discuss more in the next lecture. Fine. So I'm closing this session here. Okay. Have a nice day.